Thanks for coming today. This is a special URL seminar, and if you don't know, I'm Aimé Fournier. It's my pleasure to host Boris today. I have a project with Equinor, which is related to trying to do measurements to estimate pore pressure anomalies in depleted reservoirs ahead of the drill bit without VSP or other measurements which might make that feasible, but we always to do it by some new technique. And I've had this project for about a year and a half now, and you know, Pawan is my postdoc, and Niels Covey was my postdoc, and now we have a new postdoc, Charles Henry. And part of that project should involve more understanding of rock physics, and so we've been focused on almost everything else than that. But we've moved to a point in the project where we hope to understand more about how a better understanding of rock physics could inform the data processing and remote acquisition for this project. And so it's very timely that Boris was invited to visit. He has been here before, as you probably know. He was had a sabbatical here about 4 years ago, and is very interested to have more collaborations with us and maybe visit more often or somehow interact. If you don't know, Boris is professor of petroleum geophysics at Curtin University, and he's been there since 2001. His biography is part of the invitation to this, so we'll spend more time on that. But we're very pleased to have him give this talk. His title is Seismic Attenuation and Dispersion in. And I've warned him that we like to interrupt and ask questions, so he's ready for that.
Thank you. Thank you, Amy. This title is a little different from what was written in the announcement, but it's exactly the same talk. It's just you can have a longer title and a shorter title, and the Curtin template doesn't allow too long titles, so it had to be short. But to be honest, it's a retrospective of some of the work we have been doing on this dispersion attenuation and in porous rocks, and I might try to squeeze in more material than I can, but I'll cut me short. I'll start with the issue. We published a paper in the in the jubilee year of geophysics. A review of seismic attenuation and dispersion resulting from wave-induced flow, and basically that paper is actually has been surprisingly popular. So popular, in fact, that it's is the most cited paper in geophysics since 2010, and it's a review, so it's not an original work. But it just highlights the interest in that topic, not because we are smart writers or anything. In fact, I really don't like how this paper is organized. But the readers, it's very widely cited because it is and shows that there's a lot of interest in this topic in geophysics. Even though you will say geophysics is the core sort of seismic journal, this is probably not the mainstream topic, actually, you know, the rock physics. But basically. What it is basically a wave propagates through a rock, and simply speaking, because it has fluids and solids in it, they move with slightly different particle velocities, if you like. That creates dissipation, and that is a source of viscous forces because of the relative movement and the relative movement, and so it has to be somehow studied and affects our observations. Now, I'll give you later on specific data examples where this is manifested, but basically we study this on 3 scales, if you like. The pore scale, the mesoscopic scale, where we talk about heterogeneity is much larger than the pore size and it's smaller than the wavelength. And we also talk at the wavelength scale processes. And I start with with this one, and basically the biotheory, which is now over 50 years old, basically considers that when you have a wave propagating through the system, the porous system, you have peaks and troughs in the wave. On the scale of the wavelength, there would be pressure gradients on that scale between fluid in a fluid, and these pressure gradients will give rise to some relative movement that will cause attenuation and dispersion. Now, if you study this carefully, and I really don't want to go into that too much, well, in fact, not at all, then put math to it, then it turns out that for typical rocks, the characteristic frequency of this kind of processes is around 1 megahertz, so in the megahertz range. For very, very porous permeable rocks, that would be maybe sub-megahertz, but still way into ultrasonic frequencies. So what's happening in the low frequency is interesting, but before I do that, I say for many years this remained as a mechanism of attenuation, a kind of enigma in terms of because it's such a high frequencies, you can barely observe it in some very careful laboratory measurements, but what about in the field? Well, now in the last 20 years, actually even a bit more, there is some evidence of this mechanism in data, and that's the only slide about this particular mechanism that I'm going to show you. This is the actual data that was published in the last decade, and shows the predictions of the biotheory as lines and data points as data as symbols. And this is data from recent ocean sediments, of which I wasn't aware until I was here on sabbatical and visited the Acoustical Society of America conference in Providence, Rhode Island, and I discovered that the acoustics people, as opposed to geophysicists or exploration geophysicists, actually have kind of relatively reliably match the data to the theory on attenuation. And the reason, of course, that this is quite prominently, you can detect this in the recent ocean sediments, is because they are very highly porous, so this mechanism scales with porosity, and permeabilities as such, they're not like in rocks. They are orders of magnitude higher, and therefore the characteristic frequency shifts to a kilohertz range rather than megahertz range. So because it's all controlled by permeability. I could give you some scaling relationship. It's very easy to show that this is the characteristic frequency is related to permeability directly. The higher permeability, the lower characteristic frequency, and that's around several kilohertz here. And I wasn't aware of this. These studies have intensified in the 1990s or late 1990s with the end of the Cold War. The interest of the US Navy shifted to shallow seas rather than oceans, and that prompted some interesting marine experiments that were carried out, and this is a review paper, and there's lots of interesting work cited in this paper, and so that's all I wanted to say about the global flow, and I'll then say the more relevant to the seismic sonic sort of world is this mesoscopic flow. Basically, the physics here is that you have sort of regions in the rock with saturated with different fluids, for example, like patches of fluids, maybe better shown in which are smaller than the wavelength but larger, much larger than the pore size. So so basically, this is, say you have regions of this kind of large, regions where you have softer and harder parts of the rock. For example, medium 1 is stiffer, medium 2 is softer. So when the wave propagates through this, compression will cause the fluid to squeeze from more compressible parts into less compressible parts, right? So kind of physics is very clear. These objects may be very small compared to the wavelength. They have nothing to do with wavelength, in fact. They're quasi-static in that sense. And so this occurs in much lower frequencies. Now, of course, it's controlled by the size of these, and some characteristic of the medium as well, which is a fluid diffusion length. But what we discussed, and this was, I was studying the mesoscopic flow from, shall we say, 1980s, theoretically, and that was part of my PhD. In fact, but later on, when I tried to move away from a pure theory and look at actual rocks, I realized that basically only significant is mesoscopic flow when you have strong heterogeneity. And when I mean strong, it means the variations in properties, spatial variations in properties, should be strong. And moreover, it's actually quadratic in that strength, quadratic, not linear, but quadratic in that strength. And so if you have a little bit of heterogeneity, every rock has, right, on all scales. But if it's 10%, it's not gonna, it would be negligible effect. So kind of the interesting cases which we studied is, one is patchy saturation, and basically have, say, gas regions that are saturated with gas and regions saturated with water, for example, and of course, or oil, and obviously the contrast is massive between these two. So that's where these things are important, and we know it from seismic data in gas fields, in particular gas chimneys and stuff like this. Although no one has actually shown whether that's an effect of patchy saturation and this kind of mesoscopic wave-induced flow, or actual scattering. And more work needs to be done to clarify that. And that's how we are disconnected still between theory and experiment. The second case which we studied, and we've done a lot of work in that respect, several, and then in porous fractured rocks, we done a lot of work. Fractures are obviously a high contrast heterogeneity, right? So very high contrast. So this is another case where you can have a significant attenuation and dispersion due to presence of fractures, fluid flow more precisely between fractures and the porous rock. And I personally supervised 3 or 4 PhD theses just on this topic. The most recent one is just finished. A very brilliant student who connected actually theory and numerical simulations. And why it is important? Because theoretical work is limited to very simple systems of aligned fractures, whereas the numerical work allows you to model all sorts of fracture systems. And we have shown that what they observe in numerical simulations we can explain theoretically when they have simple systems. So that's all consistent. So that's just one student graduated just recently. But I will not talk about this either today, because otherwise I'll never finish. So what I want to focus on entirely today is the pore scale stuff. Okay, and pore scale stuff is interesting because it always happens. It cannot. You cannot find a situation where it doesn't happen because, particularly if you have compliant grain contact. So perhaps if you have a very stiff carbonate, that would be relatively minor. But if you have any sort of typical granular rock, be it clastic, sandstone, or carbonates, but grainstones and stuff like this. You will always have this kind of mechanism. Basically, the mechanism that we talk about in this context is called squirt flow, and it's basically a pressure relaxation in the grain contacts into the pores. So the grain contact area is like a crack, if you want. It's not really a crack, and the rock doesn't have to have real cracks, but it's always like a compliant thing. And so when this compression happens, it squeezes out the fluid into these pores. When the compression is slow, it easily pushes fluid out, and we have a pressure equilibration between these contact areas and pores, stiff pores we call them, to distinguish from compliant grain contacts. And when it's fast, there's no time for this fluid to move. That means the system is actually much stiffer, and that's all what it is about. So you have a dispersion. The fast, the high frequency is stiff, and slow, low frequency is soft. So let me discuss it in the context of some ultrasonic data. So here we have this kind of system, and you have these squares, measurements of the dry bulk modulus of the dry rock. So because we have compliant grain contacts in a dry rock and low confining stress, grain contacts are soft. Now this increase of the modulus by 20% in a relatively small pressure range is an indication that you have soft contacts. It's not something that we imagine or we look at the thin sections. We actually see this in this stiffness. You know, if you look at the intact material like metal or quartz, you will never have this kind of strong stress dependency of the properties. The stress dependency of the properties means that you have a very compliant pores. Moreover, it can be shown that if the pores are closing at say 50 megapascals or at some pressure, then the aspect ratio of the pores that cause this closure of cracks is, roughly speaking, a ratio of that pressure at which it closes to the modulus of the rock. So this is like 50 megapascals divided by, say, the modulus of the rock itself is 20 gigapascals. So we have about 10 to minus 3, a bit more. So 2 to 10 to minus 3 aspect ratio. And that's what these contacts are about. They're typically, the aspect ratio is about 10 to minus 3. Or lower, depending. Of course, it's just a rule of thumb, right? Because there might be a smaller here and larger here. But just as a global rule of thumb, that's about 10 to minus 3, give or take. So it's evidence of the compliant pores. And then in a liquid saturated rock at low pressure frequencies, the fluid pressure can equilibrate between compliant and soft and stiff pores, and contacts are still soft. So the Gassmann, this is a Gassmann equation prediction, which assumes that the pressure is equilibrated throughout the fluid pore space, including compliant pores. And so it's more or less parallel to this curve. Not quite parallel, but it's still strong pressure dependency of the liquid saturated rock. However, at high frequencies, the pressure has no time to equilibrate. Basically, compression causes these pressure gradients, but there's no time for fluid to move. And so concepts are much stiffer. And we have dispersion. And so the circles here are actual data measured at ultrasonic frequencies in the same rock. And you see much milder, if any, pressure dependency of that. And that's experimental evidence. That's not theory or anything. The theory is the blue line, and that's the high frequency theory. But perhaps, and there's hardly any pressure dependency in that one. In the circles we have a tiny, small pressure dependency, probably because we are not in the high frequency limit, because that limit might be a little bit higher than that. But depending on the rock, you can have cases where it plots in the middle, because it depends on what your characteristic frequency of the squirt flow dispersion is. And that's controlled by the aspect ratio of these contacts. And of course, this is a dispersion. So this Gassmann line is a low frequency line. The blue line is your high frequency line. It's called the Mavko-Gisbert theory. And confining pressure reduces that dispersion. Here dispersion is large, here dispersion is small. In ideal world. And I'll show you why I say in ideal world, because life is a bit more complicated than that. So this is the squirt flow in a nutshell, this slide. Okay? Now, I would be just hand waving unless I had extra experimental evidence. Here's a typical, it's quite unique actually, wouldn't be typical. This is effective pressure. There are some people who can measure rocks at much higher pressures than we in the pore exploration labs. Here's the measurement to 200 megapascal, not to 50 megapascals. We can't do that in our lab, but people in France can. And so, and because they are not exploration geophysicists, they are geophysicists. So they study deeper parts of the earth, they need higher pressures. So this is amazing data. This is increase of the, this is I believe a low frequency measurement. Yes, it's a low frequency measurement of the bulk modulus, and this is the high frequency measurement. This is not a Gassmann prediction anymore. This is actual measurement at low frequencies, and this is a high frequencies. And if I have time, I can show later a bit how these measurements are made, because we also have a lab that measures this. But the beauty of that particular machine is that it can measure up to 200, and you see that dispersion decrease. This is the direct experimental evidence of squirt flow. And by the way, I proud that now I connect every theory to some sort of experimental verification, just like I showed you the biotheory and the ocean sediment data. And there are now many more of these kind of experiments. At that time, when I put this together, this slide, this was the only one. But there are other data sets, particularly from that lab, but also from our lab and a couple of other labs, showing similar sort of behavior. So I basically, this is the same slide, it's just repeating the same stuff, but now with experimental data. We have developed back in the 2010 some theory which basically considers, based on is largely on the theory of that Bill Murphy developed in the 80s, where the fluid is in the soft pores and the stiff pores are first dry, and this relaxation of this kind of grain contact, if you like, simplified, it actually gives rise to a relatively simple analytical treatment. I'm not going to spend too much time on this, but just to say this is a two-stage process. We look at relaxation in this kind of context with the boundary condition that the fluid pressure here is 0. And once that is done, we kind of look at this as a new modified dry modulus, and then we use Gassmann or Bio equations to fill the stiff pores. Okay, and we will see through my talk the other cases we use this two-stage process. Now, the inventors of this two-stage process are Mavko and Gisba in '91. So this is not our invention, but it's a very powerful way of dealing with this kind of models. Okay, it assumes that these little the contact pores are tiny, so the contribution to actual overall porosity is small. So the expressions that we get that are theoretical for the model, for the models of such system, are relatively simple. And when I say relatively simple, the equations might look, but actually they're extremely simple. So they are simple analytical expressions. They're not vast programs that some other squirt models have, and so we're proud of that simplicity. But it do have some parameters, if you call them some parameters like aspect ratio and the overall volume of the compliant pores, and they need to be inferred from somewhere, and they can be inferred actually from the observation that actually your modulus itself, this dry modulus, is actually depends on these parameters as well, because that dependency that I showed you of the stiffness of the dry rock, as I told you, is controlled by the aspect ratio and by volume of these compliant pores, and that was actually observation of Walsh back in the 60s, and there's some methods how you can do that. It's not exact science, but it's a good ballpark estimation of these parameters. Now, when you actually try to apply, these are just predictions, maybe not so interesting, but when we actually apply this, unfortunately, we discover. Oh, maybe I missed one slide. 1 second, give me a sec. Oh, oops. Oh, why this? Okay. So I'll just. Yeah, I unfortunately I thought I missed one slide, but anyway, what I want to say is that. Okay. Takes a while to get it back to the screen. So what actually happens when you start looking at real data, you have sometimes discovered that, maybe I'll show you on the previous slide, that, this is the slide actually, sorry, that sometimes you get at high pressure, your data point is consistent with the Gassmann prediction, okay? But unfortunately, or maybe even, it's not always the case. In our 50 megapascals here, your low frequency measurement is not quite consistent with high frequency measurement. Basically, the pores close, the compliant pores or whatever causing pressure dependency or squirt flow, they are not closing in this 50 megapascal. You see the data, 50 megapascal, the way to go, right? And what happens means for us, and sometimes it's a lot more like this, more curved. And what that means is that we need to account for kind of two scales of this compliant porosity. And that's what we did here. So this is conceptual thing. This is actually a range of the measurements we make in 20, 50 megapascal, and that corresponds to the very compliant porosity. Then there is this intermediate porosity and the stiff part. Unfortunately, that's life. And when we apply this concept, the stiff porosity, intermediate and compliant, and somehow fitted the data, we got okay, we're stuck here for some reason. Oh no, that's okay. We got a reasonable prediction. So here is lots of sandstones. These are moduli from ultrasonic velocities. These are predictions of a squirt flow model. There's no adjustable parameters there, otherwise everything will lie on this line. And basically the crosses are the Gassmann predictions, the empty circles are the Mavko predictions, the high frequency sort of, and our predictions based on inferring all these parameters from dry data, not directly fitting the saturated data, is these field circles. So for clean sandstones, this model is reasonable. Has lots of parameters, but they are not fitting the fluid saturated data. They are only fitted from the dry data. And this is something that we were proud of, because most people, when they do this kind of modeling, they look at a couple of rocks, not like 100 of rocks. Yeah.
How come the filled circles have so much structure? Usually a model produces something that you can see the pattern in right away, but these have a lot of detailed structure. I just don't understand how they're a prediction.
What do you mean by structure?
So I see some circles that are close to a line. I see some circles that are off the line, making a little pattern here and there.
Well, these are some fundamental sandstones that we don't fully understand why they're behaving this way. So you know, we have a concept of different range of porosity, confined porosity, and this is a simplified description of the pore space.
So
it applies to some rocks and not the others.
The simple answer would be that the same marker is for different kinds of rock. So there's a hidden variable here besides. I was trying to figure out if it was just a saturation effect, but obviously it's not. It's different.
No, they're all saturated fully.
Yeah.
So the question is that they are all at different frequencies. No, frequency is the same, but they are sitting at different places in the frequency range because of the characteristic frequency varies.
Okay.
Are the different dots distinct samples?
I don't remember. I've been asked this question before, and I don't remember. I have to go. I don't want to lie, and so I thought it should be, but maybe they're not. You know, so I have to double check it. It's in the Osni Dipola. It's a thesis of this guy, and I have to go back to the thesis and look at that. So it's a good question, but I don't remember. Probably not. Probably there's some clusters of same rock.
But we should be comparing the filled circles to the.
That one's good.
Yeah, so the filled circles are better because these underestimate, Gassmann underestimate, which is not surprising, the modulus. And the Mavko overestimate, because you're somewhere in between, but that in between, you know the frequency, you know the permeability of the rock. So you can actually compute this dispersion, and it kind of helps. I'm not saying this solution is perfect, and it's good it is not perfect, because otherwise we're cheating ourselves somewhere. But they're better than the predictions of the known theories.
But we're comparing three predictions.
Yeah.
We're not comparing, there's not a measured value. Yeah, okay, that makes sense.
No, this is measured and these are predictions. Yeah.
Okay, so it's really that.
Yeah. So the ideal world, they should be all.
Got it.
Yeah, but they're not always. Much worse for when we take the entire Hans data set with all the shaly sands. This was a clean sand, now this shaly sand. And you can make your mind whether that's a better prediction than, on average they're better, but that's called comfort. It's like called, in Russian it's called average body temperature in the hospital, you know?
I like this one better than the last one. Now it's very clear what Eme was asking about.
Yeah.
There are two things visible. Most notably, that connect there at 25. There is a trend that is shallower and a trend that is steeper, and there must be some story about what is the population that's got one slope and what is the population that's got
I think
the other.
I think a lot of rocks still.
And it can be a story about the protocol that was in the experiment. It could be a story about what was the sample that was experimented upon.
Well, the good thing about this is all from one experiment, one experimental lab. It's not from different labs. It's all from Stanford lab. It's all Hans 86 data set, and so experimental protocol is exactly the same. But of course, samples can be handled differently. I'm not, but I think you're right. It's probably same rock plotted for different pressures. They're for different pressures, you know, and that could be, and maybe we need to clean this up. But
or is it a theoretical one story for one set and a different story for a different set? No, but black dots are.
They're all three predictions against the measurement. So the good theory should always plot close to this line.
Yeah.
And ours on average plots closer to this line but that's called comfort for individual rock.
But you might hope that there's some other variable that you can make the pure theory collapse.
Possibly, but you know what Doug said? Shales are bloody. No, it's Eve. Are bloody difficult. It's not quite shales. They are sandy. They're shaly sands, but they. Well, I would say like this. You heard my concept of pore space, right? That concept definitely cannot apply to when you have clays.
Boris, they may not be dry. The ones with
Oh, that's another issue. Yeah.
I mean, then it would not plot on the.
Yeah. So none of this is dry, but you obviously understand that all predictions are inferred from the dry data, all the parameters, you know? So if I say Gassmann theory, it has, Gassmann theory uses dry measurements as the building block, whereas our theory uses dry measurements, obviously, as a building block, but also parameters inferred from dry measurements are pressure dependency. I'll claim that probably okay, even with the presence of some moisture, but we can.
Do you account for two pressure dependencies, one for the clay and one for the pores?
Oh no.
Could
It's
that
just
have
a rock.
something to do with this?
Probably.
Yeah.
No, the rock that's all we can measure. You know, you take a rock and measure. You know, a pressure dependency on that rock.
I like this slide very much, and the question, good theory, good experiment. The slide is showing data that clearly distinguishes two distinct populations of black dots. Well, more than two, but three are clearly there.
No, you're right.
If we go to the paper, will it describe fully what's being plotted?
I don't know about in the paper, but certainly in the thesis, yes. I'm sure the paper does as well, but I'll give you that. Yeah, the paper is written here, the reference, so it's all there, and you have all the slides. You can have all the slides.
The slide isn't what I want. I want the description of how the
the slides have references.
Yeah.
Don't worry, has references.
It's a good time for a rant. We're at MIT. People are always telling us their conclusions. I cannot understand.
But otherwise we talk for 2 days.
What they've learned unless they tell me the protocol that they followed in order to prepare this. There are two sides. There are two sides to this. No, there are two sides to this. Our protocol is explained in detail in that paper, and if you have more questions, we can send you the thesis. Enhanced paper, which did the experiments, is also available. It's written very carefully. It's experimental paper, so anyway. Now I want to shift from a fluid-saturated rock to rock saturated with more complicated substances like heavy oil. Okay?
Yeah.
Because I'm still in the middle of my talk. It's not. These are measurements. But I'll try to be quick. These are measurements of the oil, heavy oil, which shows dispersion of the shear modulus, changes with the frequency, and changes with the temperature. This is temperature change, and similar changes in the rock saturated with that oil. Okay, these are just measurements from Jyoti Bikura, and basically our theory ideally should account for. We have to have theory from fluid substitution, how the properties of the oil affect the properties of the rock. Obviously, what I told you before doesn't apply to this because there's no pressure relaxation in a simple way. The Pascal law doesn't work once you have viscoelastic material, finite rigidity and stuff like this. And here is replotting the same data. This is oil, shear modulus oil at different frequencies, different colors at different frequencies. There's a temperature dependency. And these are oil, rock with oil. These are all data. There's no theories here. And what is remarkable here is how little changes in the modulus of the oil itself affects greatly, disproportionately, the modulus of the rock. This is not a Gassmann effect that gives you 10-20% or anything like that. This change of the modulus here changes by at least 1 order of magnitude, you know, while the oil changes are just like less than 1 gigapascal. And what's causing this? Basically, imagine. Basically, we saw that you know, this oil changes from liquid at high temperatures to almost solid at low temperatures. And if you have a contact like this and you have liquid and you have sufficiently low frequency, it will squeeze out. But if it's solid, it's not going to squeeze out even at low frequency, right? So this is a very similar to squirt effect, but controlled by not by the aspect ratio of the pores or characteristic frequencies of the pores, but characteristic frequencies of the oil itself. So I think the first, I've gone too far. Yeah. Anyway, so this is actual effect that first observed by Larry Dworkin, and I'll not switch back and show you the slide because that takes time. But this is another type of squirt effect, if you like, which is not dynamic but quasi-static. And finally, I'll show you the model that we use to model both. Actually, both can be modeled with this little simple system. So you have a grain contact, not through all these solution and Navier-Stokes equation, whatever. It's actually simpler. Here is a solid between the two plates. These imagine 2 grains, okay? And you compress them like this. They are opening to these open pores that are not shown here, okay? And basically you solve the problem of elasticity for this kind of system with finite aspect ratio. And then you can use elastic viscoelastic correspondence to actually get your fluid-saturated rock or any for any pore field. So the solution of this. Now the solution of this problem. This is the classical elasticity problem. It was posed about 100 years ago, a little bit more, 120 years ago. It was actually not solved until relatively recently. So the solution, approximately a very accurate solution of this problem, was actually by Tsai and Lee, who verified their solution with numerical simulations. And obviously, when it's a fluid, the stiffness of this system is 0. And when it's very tall, this thing, then the stiffness of this is Young's modulus. But we're talking about a finite aspect ratio. We are certainly not talking about a very tall system. So people sometimes apply the concept of Young's modulus to a finite, like measured sample, and you don't even think that they actually, strictly speaking, only applies to very tall cylinders. And that's because that solution works. Actually, it's quite accurate, except where you get close to the fluids, to Poisson ratio close to half. And then that sort of breaks down. Then it becomes very sensitive to aspect ratio. And that's the trick you need to be aware. This particular solution by these guys, which is on the next slide, I believe, somewhere written, these are also shear. Here is the actual solution here, which you don't need to write down, but it's a really, really simple, and it's basically verified to be accurate, close to singularities, close to the Poisson ratio equal to half. So it's actually verified, and with finite element modeling and stuff. And so this solution, I mean, if you now have, instead of solid, a liquid, you just write is a complex shear modulus of I omega eta, where eta is a viscosity, and omega is your frequency, and you get solution for the squirt flow for free. In fact, we have shown that that solution is exactly the same as in our previous solution that I showed you, but it also applies to viscoelastic materials. So let me be quick. So we use then using this solution, we get this normal tangential compliances, which we put into the Saxena framework, considering like a cracks, and then we apply the Shapiro equation for stiff pores, because stiff pores have also material, and this is a generalization of Gassmann. But don't apply this to the entire pore space because it won't work for compliant pores. It assumes that pressure is the same in all pores, and pressure is not the same in compliant and stiff pores. They're very, very different. So you can only apply to roughly where they're the same. So these are two-step process again, and these are some curves that show a solution for different situations, and where the squirt flow as a function of frequency, basically modulus and attenuation, and it covers the squirt flow. It maybe that's written actually somewhere. Yeah, this is squirt flow, and these are shear relaxation, which you don't get in our squirt flow theories. All the other squirt flow theories get direct shear relaxation here, and then I have experiment that actually verifies this theory, but I basically only say a few words about this experiment. We have found a material. It's actually petroleum engineers from our university came up with we pose them a task, find us the polymer or something that will melt in convenient temperature. So it will be solid at one, not viscoelastic, solid, elastic at one temperature, and those temperatures where you can make experiments. So it's about 28 degrees centigrade, the melting point of this. And so this is solid. After decaying, you don't see much through. This is a liquid. And so we put that into, and these are velocities in this material. So P wave velocity drops around 28 degrees, and the shear velocity disappears, shear wave disappears. Of course, I should have put some waveforms as well, but and
I thought you were going to say you could use butter.
yeah, but butter is not really crystalline solid, right? And these are some data, and we're fitting them and find more stuff. But I'll stop here, actually. The other thing I wanted to show you, we also worked recently on, not so fast, right? I don't want to, there's a lot of work here which I can't show because of the interest of time, but I'll just go straight to the next section. This is fitting this model to the Uvalde oil that I showed previously, the viscoelastic, using and it kind of fits okay. But what I really wanted you to show also that we also worked on the exact bounds for attenuation and dispersion. I mentioned that in the abstract, so I must show you that the final slide only. So this is the final slide. We have derived exact bounds for attenuation and dispersion for fluid-saturated rock. There are more general viscoelastic bounds exist for that are due to Milton and Berryman and Tibersky, but we derive these bounds for liquid Newtonian fluid-saturated rocks, and these are exact bounds in complex plane. You know, the Hutchins-Strickman bounds are intervals of a parameter, right? Bulk modulus must be between A and B. Here, because moduli are complex in viscoelastic media, bounds are areas in the complex plane. And so these are the bounds, these are bulk modulus, and these are the shear modulus. and we derived analytically these bounds. They are semicircles like this. And the dots here are predictions of our squirt model. So the latest squirt model. This is entirely the different curves are for different pressures. And so we proved with this that they actually fill these circles. It means the bounds are exact bounds. They can't be any tighter. And this is squirt flow, and this is squirt flow, and this is viscous shear relaxation. And when I gave this talk some years ago, I did not have this result, so I only had the squirt model, and so I said this bound is exact bound for bulk modulus, but for shear I don't know. Maybe there's a tighter bound. And then I realized that we missed the viscous shear relaxation, but with this model, with this, which is more general than just the liquid thing, we actually covered both phenomena, and we showed that this is exact bound as well.
So it's comparing, just to simplify, it's two kinds of calculation that are being compared. The asterisk is, I mean, they're both predictions.
These are bounds,
Yeah.
so they don't assume any specific geometry of the rock at all.
Yeah.
Just a mixture, the fluid fraction, the solid fraction, and so on. There's no, so these are bounds.
Right. But what are the
The others are actually predictions of our model. Now, the geometry is specified. So I told you, we have stiff porosity, blah blah blah. But this is actually the model.
Okay.
And the geometrical model we assume for these curves. So
And are the bounds derived from analyzing that model?
No. The bounds are completely general.
Got
They're
it.
just nothing. I should have said, because unfortunately it's a separate sort of talk. But the bounds do not assume anything about geometry of the rock. The model actually does. And the model to fit in here, it must be a Hessian sphere assemblage penetrated by cracks.
So you're working on some measurement confirmation, you see?
Bounds.
I mean, it'd be great if we could put data inside those bounds.
Yeah, we did this. So this is actually hot, ongoing topic. Sometimes they don't want to plot inside these bounds, and sometimes they don't plot even normal Hessian frequent bounds. The low frequency measurement that really applies to all quasi-static. These bounds are quasi-static. That means a BO theory scattering is not covered by this. So they're quasi-static. The mesoscopic flow, which I showed, the squirt flow should plot between these. So for this, to put data into this, you need actually low frequency stress strain measurements, on which I have slides. And like I showed you some data. But low frequency measurements are work in progress. So that people, you ask them why you're plotting outside this or outside that, and I say, that's work in progress. There's some things that happen, and this is still kind of developing. These are exact theorems, if you like. So I don't need really data to verify that. However, the data needs this. It's a quality control.
You might say you need the data to make them relevant. I mean, they're exact theories.
Absolutely. But so far, this is more theoretical sort of thing. All right, I'll stop here. Okay, thank you.
Thank you. Very good. Well, that was a lot of information
Yeah, sorry.
presented. No, but I think you responded and presented. Really covered. There's a lot to ask about, I hope. So I have a question that I can go back to, but I want to first see who would like to ask a question before.
I have a question. Would you go back to the slide about the material that isn't butter?
Yeah.
Octobutane.
Because it was another one that had something going on, and same question again about what's the story about the
It's coming.
because I think it's another place where we can understand better the protocol that's giving rise to the plot. There. So some of the blue dots don't curve down. Some do curve down, and then they come to this
Okay.
stable
The
thing.
maximum level is
And that must be a protocol or
I know, I
a
know.
time of, where we're repeating, but it didn't repeat. It's mostly the ones.
It's a
on the
direction.
top.
It's in one direction, and this is the other direction.
So it's
So hysteresis.
Wait, no, I'm asking about those guys.
These ones.
Those ones, yeah.
I tell you, this is a hysteresis. It goes down and then up.
So he warmed it and then he cooled it.
Yeah. So there are two temperature lines. So we.
It's multi-valued in temperature.
So how we avoid this? We actually look at data here and here, not here,
Where it's a function.
because we assume that this in this kind of that melting happens instantaneously, but it's not, you know.
No, but I'm starting to understand. 1,500 meters per second as a stable P velocity when I don't have any shear velocity that I can measure.
This is actually nice because it's almost more.
That's a liquid. But up there at 25 degrees C, we've got some decay that's not abrupt decay. It's the
Yeah.
decay that is not abrupt decay. Is this when the material is, well, again, it's the protocol I look for, because I imagine that if we're melting butter or something like butter, that there's, or going the other way, well, I've watched cement dry, you can see the onset of shear, but there must be a story about that path, and it doesn't seem to be collected.
No, but I tell
You're
you,
saying
it's
that
just a different.
it jumps from the stable liquid up to that point?
I don't remember actually which direction, so we can have a look.
Yeah.
But if it's a heating and cooling cycle,
Exactly.
then that's, there's morphology, there's a lot of stuff to understand.
Yeah. Look, the rock is a good thing. Well, in my slightly different work, I'm working on pore elasticity of nanoporous materials, and stuff that happens in the tiny pores, the actual melting point actually shifts.
Yeah, you said 28, so 28 is right where it happens.
Yeah, but I don't do my head on that. But what I'm trying to say is that material in the pores might have slightly different. I mean, we probably not quite at that nano scale limit, but there's some compliant pores that are kind of, this might be small pores affecting the melting. But I think it's more practical that the melting is not instantaneous across the sample, in terms of I'm not in. There's worse. Something is worse. I'm not 100% convinced that this stuff is a normal, classical crystalline solid that that really melts sharply the phase transition at one. So this might be amorphous here or something, and only here it looks like a crystalline at low, but we have some debate. My ignorance as well. I need to look more into what is it actually.
So if there were
it's actually solid for more intensive purposes, but is it really polycrystal? We have to look at that.
So during the phase transition, there could be a liquid-solid mix.
Well, it should. But for a normal material like this, and this is not. No, I was saying rubbish. Sorry. This is a pure opto-decay. There's no pores. I got myself confused. So it's actually this hysteresis is inherent in the material properties. So it's not, unfortunately, a simple, material like water, which is not simple either, but because it gets tricky around zero, right? It's expanding and stuff. But some materials just have a very sharp melting point, most conventional. But this is polymer, right? So this is a hydrocarbon, So it's not quite a simple crystal. Ideally, I should have worked with that. Solution is really not working in this region.
So what would be very informative for somebody like me, those dots are extracted from waveforms, and there was a continuous process that went on, one waveform per dot. If we had a variable intensity plot of the waveforms,
Yeah.
and they
We
could
can have
have the
that.
dots placed on top of them, and then there could be a cross plot of temperature against
Yeah.
velocity. But it would be very interesting to look at the waveforms, and we would see this coherent thing up there as either some feature in the picking out of the waveforms,
I mean, you're
or
right.
some feature in the change in the waveform as some material critical point,
Yeah.
which we
You've
could
got
call
software
the
to analyze
onset
the
of-
data.
But
Yeah, you're
but
right.
the waveforms here would be very informative.
Yeah, probably. But what else? Yeah, I agree. I even said that before you asked the question, but it would be nice. But you know how democracy works. You know, this
That
was
doesn't
presented
work.
a dozen times at least, and no one ever asked this question. but it's like by
That's why you
popular
came here.
demand, I will have to remember it because I think it makes sense. It wouldn't take too much time, and we can have it in the appendix if someone interested, rather than in the main slides. But I think it would be useful to do that. But I
We
have
want a
way too much
collaboration.
anyway.
Doug's offering to analyze the data. That's what I
Certainly
heard.
that much data, yeah. I mean,
No, but this
you
is-
give
this is-
me 100 waveforms, I give you a picture.
But this is not essential to this talk, but I have to explain it. Yeah. All right.
If
all
it's
right.
in D-list, then it's expensive.
More questions?
Who else has a question?
You had the question.
I had a question, but I need to go back through the slides to see what it was, because I can't.
Do you want a kind of a
Can you
picture
just-
of all slides?
Well, just go back and I'll tell you to stop, or then I forgot.
Back, right?
Yeah, it's not ahead of this, it's behind before this. Oh yeah, this was actually it.
Okay.
That was lucky.
Okay.
So I was just trying to understand.
I can skim through. I know I've skimmed through. Yes.
So I'm interpreting this as some kind of a resonance effect because I have these bumps versus frequencies. Is that
No, they're not resonances, but like resonance because they're not really sharp resonances.
not-
Yeah,
but
yeah,
they have
but they are classical sort of dispersion attenuation pairs. They're like viscoelastic relaxation, if you like. You know,
So
they are
they're-
basically all viscoelastic relaxation.
So, but there are different frequencies
Yeah.
for the
Yeah,
different.
yeah. And this is actually look at the classical paper Konrad-Budiansky lays this out. I believe they have both squirt flow, which is controlled by the aspect ratio. Actually, scales with the aspect ratio cubed, and the viscous shear relaxation scales with the aspect ratio in the first power, as I remember. I can't even.
But an equation like this. So this.
No, this is just a simple, some crude equation for a viscoelastic material that somebody came up with just to write. It's not really.
But that's a viscoelastic material, that's one viscoelastic.
Yeah. It's just a good
material.
example.
And when you're building spring and dashpot materials, if you put in two dashpots, you have two time-dependent pieces of physics,
Yeah.
and they will each give rise to a transition.
Right. You can almost.
And,
I mean,
if you do that all in 3D with Sayers and
But what I'm trying to say.
then you get the whole thing breaks down, and either you have a blend or you have peaks that
Yeah,
pick
so
out the components.
This is a liquid. This is liquid, generated to the clear, and this is the Uvalde oil, a crude approximation of Uvalde oil, a crude approximation. Okay, so here we have squirt flow and we have shear relaxation, but in shear modulus we don't have squirt flow in this material. This is a particular example which is not probably. Usually you will have, and then the main transition side in a here, and it's more complex than I expected actually. But the purpose of this was to show that this model is very rich. It actually
Yeah.
describes all these phenomena in one, and it's simple equations and not really complicated. And for example, I'll show you this. If you look at this kind of thing, right? In the limit of low aspect ratio, which we are mostly interested, low aspect ratio, this is actually can be considered an isolated crank. Because the very similar result. So actually, for most solids and most even viscoelastic materials that have finite shear modulus, even small, they are equivalent. So the Mavko Saxena and Mavko model almost equivalent to our model, except in the transition, it doesn't describe, if you do gasolytic corrects, you will never get Gassmann limit, you'll never get a liquid squirt. So you will always be in the high frequency limit of that squirt flow. So that might be, so for heavy oils, for again practical purposes, that's probably all right. But it doesn't have the phenomena that we describe when you actually open these pores into the material. Because this is close to the solution of the gasolytic correct, except when you have liquid. The transition in the heavy oils is tricky because you really heat it up, it becomes Newtonian liquid.
Great. Are there any more questions?
Yeah.
Just one simple question about the first slide. You have this very unusual looking rock. Can you tell us that?
This already was asked before. This is some sort of ceramic.
That's a
It's
ceramic.
not really a rock.
It looks like a pancake.
It's all, it looks like an oolite with a quartz cement with the oolite.
I probably need to update this because this slide was created back in the 90s where internet wasn't very rich. So I found some things
So
on
I know the
internet.
answer to my next question, and I will ask it.
Where did you get
That particular slide, I got it from internet.
But it is very regular. That's what I
Yeah.
did. It's a very regular
Yes,
crystalline
ceramic.
kind of
It's not a
pattern.
real rock.
Ceramic.
I've never seen it.
It looks like it's a dual rock, because if the things that look like the solid parts there are thought of as the pore throats.
I thought it was cement in a oolite.
I don't remember, but if you say, I asked that question before, that's great, because that wasn't today, it was some other time when Boris came.
No, it's fine. So I should have updated this, but I mean, lots of these slides are very new, but some are old. So there's